Greetings, this is the term project for the AIFA course. We will be giving a presentation regarding the interpretation of a research paper based in the domain of computer science. Hi, myself Atulya Sharma, and this is our group. Moving on. The problem statement that we have chosen for the same is stepwise explanations of constraint satisfaction problems. We would explore the problem of explaining how to solve constraint satisfaction problems in a stepwise manner while also explaining those steps in terms easy enough for a person to understand. A quick revision: constraint satisfaction problems, or CSPs, are mathematical questions defined as the set of objects whose state must satisfy a number of constraints or limitations. The main challenge here is to find the best possible sequence of steps taken to reach a solution. Here, best refers to as simple as possible. So moving on, the motivation for this research is that we are increasingly getting dependent upon AI for decision making, and the more complex the decision making process is, the harder it gets to explain the reasoning behind in layman terms so as to justify why. When we talk about solvers, the constraints for CSPs are encoded as Boolean literals. Let's take a look at this image. At this stage, even if I try to explain the encoding for all the Boolean literals for the CNF formula, it is practically unreadable. Now the problem is that SAT solvers understand this, but we don't. They are designed for efficiency, for speed, but not for understanding purposes. The cost of computation is not our concern here. We just want to maximize a different kind of cost, which in this case is readability. Every step should be simple enough to understand, and making the whole process of propagation interpretable is our aim. For representation purposes, we would be taking a look at logic grid puzzles. This puzzle consists of natural language, in this case which is English, sentences made up of entities which occur there. This set of entities is given in the form of a grid. These entities are classified into equal sized groups corresponding to each type, and the goal of this puzzle is to find relations between each such two types such that all the clues are used and all the relations are bijective as well as logically linked. Now let's take a look at the example which is also featured in the paper. So this is a puzzle about people having dinner in a restaurant and ordering different types of pasta with some unique sauce. 8 clues are given, and all of these would be used to find the solution. Note that the 4 sauces and 4 people are here. Each person chooses a unique sauce. Similarly, there are 4 prices 4, 8, 12, 16 which are mapped to both sauces and pastas. And the 4 pastas are also mapped to people. And all of these are bijective relations. Let's do a try and run for this puzzle. Let's start with the first clue. It says that anyone who ordered capellini paid less than anyone who chose arrabbiata sauce. This implies that arrabbiata definitely cannot be the cheapest, so we will put a false at the corresponding position. Now, the second clue says that someone who ordered tagliolini paid more than Angie. And this is a bijective relation. So what does it mean? This means that Angie is not the one who got tagliolini. And one more thing we can find is that Angie cannot be the one paying the highest value of 16 because someone else paid more than her. Now, the third clue says that anyone who ordered tagliolini paid less than a marinara chooser. This means that tagliolini is definitely not the costliest. So we will mark 16, tagliolini as false. And this also means that tagliolini is not paired with the marinara sauce. So we will mark this also as false. Let's take a look at clue 2 again. Someone who ordered tagliolini paid more than Angie, which means that someone definitely did not pay the least amount. So we will mark tagliolini, 4 as false. The fourth clue is just straightforward, so we will just mark false at puttanesca sauce, Claudia. Clue 6 is also straightforward. Angie and Elisa both did not order capellini. Clue 6 is also straightforward. Angie and Elisa both did not order capellini. Same with the clue 7. Damon and Claudia both did not order arrabbiata sauce. The third clue says that someone who has ordered tagliolini has paid less than the one who has chosen marinara, which means that marinara is definitely not the cheapest, and we will mark 4, marinara as false. This whole process goes on like this until we mark all cells as true or false. Sadly, this example is quite long, so we would now move on to the next section. Now we'll be taking a look at the roots of this solving method. This method is based upon typed first order logic. Kindly don't mistake this as the keyboard typing. This is category type typing. Taking a restaurant puzzle as reference, the 4 people are of the type person. The 4 sauces, for example, arrabbiata, marinara, they are of the type sauce. The numbers of type prices. The relation is mapping over different such types and each has its own signature. Like the example mentioned, chose has a signature of person cross source. First order theory refers to a set of sentences or constraints which are well formed, variable free, first order formulas, which we just covered right now. And each variable inside each sentence has a single associated type. All these definitions take into consideration that we are working in a fixed and finite domain, and the constraints are also fixed.
Hello, I am Souvik Rana, 20CS10062. So, before going into the algorithm, we shall look at some formally defined notations and phrases. With help of these definitions, we will sequentially describe the algorithm. Interpretation. An interpretation or a partial interpretation is finite set of literals such that P of d bar or negation of P of d bar, where P is a relation symbol and d bar is a tuple of type symbol. For example, consider the partial interpretation INGR, the set containing the relation choose NG Arabiata and negation of choose Alicia Arabiata. From this we interpret NG had Arabiata sauce, Alicia did not. Now preciseness. Given to interpretation I1 and I2, if I1 is a superset of I2, then we say I1 is more precise than I2. For example, consider the partial interpretation containing choose Angie Arabiata and negation of choose Alicia Arabiata and negation of choose Damon Arabiata. This interpretation contains more information such that more precise than the interpretation stated in the previous slide, containing only choose Angie Arabiata and negation of choose Alicia Arabiata. Maximal consequence. Let us consider a theory TP and partial interpretation I. Maximal consequence is the precision maximal partial interpretation J such that J is the consequence of I intersection TP. In other words, it is the intersection of all the models of T more precise than I. Now consider the sequence I0, I1, I2, In, where In equals maximal consequence of I0 and TP. If the interpretation sequence holds the property of being more precise with increasing value of I for all I greater than 0, more formally, if I greater equal preciseness than I minus 1, then the sequence is incremental partial interpretation. The goal of our work was not only to obtain a sequence but also to give an understandable explanation for each incremental steps. An explanation is formally defined as a tuple of three sets EI, SI, NI, where EI is the subset of the facts of the ith interpretation, SI is the subset of clues or constants that are used in the constraint satisfaction problem, and NI is the set of all newly defined facts derived using EI and SI. So, to find easy to interpret explanation, our goal should be to avoid redundancy. That is, we want an explanation EI, SI, NI where none of the facts in EI or constants in SI can be removed while still explaining the derivation of II from II minus 1. In simple words, it must be subset minimal. So formally, if E dash is a subset of EI and S dash is a subset of SI and E dash S dash NI also explains the derivation, then EI and SI should be same as E dash and S dash respectively. Continuing from the previous definition of non-redundant explanation, we are generalizing the non-redundancy for a sequence of tuples of interpretation and explanation. In the tuple of II, EI, SI, NI, II is elements of incremental partial interpretation and each EI, SI, NI explains the derivation of II from II minus 1. In line with the Occam's razor, we reason that smaller explanations are easier to interpret than explanations that use a large number of facts or constants. Now, the subset minimality of an explanation ensures that the explanation is non-redundant, but it does not quantify how interpretable the explanation is. To quantify the interpretability, we introduce cost function of explanation. An example of cost function can be the weighted sum of the cardinality of the sets EI, SI and NI. Now, to define interpretability of a non-redundant explanation sequence, we define an aggregate over the sequence of explanation. Explanation production problem consists of finding a non-redundant explanation sequence such that a predefined aggregate over the sequence f of ei, si, ni over all I less equal n is minimized. Now let's discuss about two types of aggregate and their peculiarities in the context of explanation production problem. Number 1. Aggregation operator max. It will take the max value among all the elements from the explanation, but while minimizing this value, we will be minimizing the cost of the most complicated reasoning steps, but does not evaluate whether there is one such step used or multiple. Number 2. Likewise, we can take average of all the F score as an aggregate, but this will favor many simple steps, including splitting up trivial steps into many small components.
I am Sharannya Ghosh, roll number 20CS 10054. So in this problem, our goal is to search for a sequence of non-redundant explanations for each step of solving the constraint satisfaction problem. The sequence of explanations should be simple enough for a person to understand. Now, this simple enough for a person to understand, this is quite subjective and often varies. But to solve this particular problem, we will quantify it by a specific cost function. And our aim will be to reduce the cost function, that is to find the sequence of explanations with the minimum cost function. Applying brute force technique is not feasible. We cannot enumerate all the explanations and take the minimum cost out of it because the number of explanations quickly explodes with increase in the number of constraints. So what we do instead is we iteratively construct the next best explanation from the current knowledge base, that is given a partial interpretation and a set of clues. We want to construct the next best explanation in the I plus 1th step from the ith step. Given towards the left of the slide is the pseudocode of the algorithm for constructing sequence of explanations. We have an initial interpretation I0 and we want to achieve a more precise interpretation IN, which is our target. For each new fact which is present in IN and not in I0, we want the minimum explanation, which is the minimum cost explanation for that. And for this we have included a function named mean explanation, the algorithm for which has been described later. The search for this mean explanation is guided by the cost function which we had mentioned earlier. Now, how to generate new facts which are currently not present in I? Now, for each new fact, we also want an explanation for the derivation of that fact. Now, we show that this task is equivalent to solving a minimal unsatisfiable core problem. Now, it has to be noted that the solution of minimum unset core problems are subset minimal, not cardinality minimal. Subset minimal implies that if one of the elements, that is one of the constraints in the set is removed, it's no longer an explanation. But there might exist other subset minimal sets with cardinality less than the one written by the MUS algorithms. We now prove the equivalence that we stated earlier. For this, let us consider the theory I intersection C intersection not A, where A is one of the newly generated facts. Now, this theory will be unsatisfiable because A has been derived from I and C, or in other words, A is a consequence of I and C. Moreover, we also know that I and C are consistent, which means there exists at least one truth assignment for that. Therefore, any unsatisfiable subset of the above theory must contain not A. Now, if it contains not A, we can also say that an unsatisfiable subset will be of the form E intersection S intersection not A, because E is a subset of I and S is a subset of C. And one of these subsets explains the derivations of A. Therefore, we can say that solving must problems is equivalent to finding a newly generated fact and the corresponding explanation. This is the algorithm for generating candidate explanation. From given partial interpretation I and set of clues, we generate a new interpretation. And for each new fact that we obtain, we perform the mass algorithm and obtain a non-redundant explanation. Now that we have obtained a non-redundant explanation, we increase our interpretations that can be generated from the current explanation, because we are assuming that facts that are generated from the same explanation use similar logic. But these new facts might have a better explanation, as we shall see later. So for each iteration, these newly found facts, the explanation for these newly found facts are updated when we call the mean explanation function repeatedly. This is the algorithm for minimum explanation. Now, we do not call this candidate generation function for the full set C, because it might be very costly. So what we do is we iteratively grow the set of clues, which this growth is guided by an optimal heuristic function G, which is an underestimate of the actual cost F for this explanation. This is because we are assuming that a few constraints will be sufficient to explain a particular step in solving the CSP. Moreover, if the number of constraints are less, it is also easier to understand and therefore they have a lower cost. It is to be noted that each time this function is called, the explanation for every existing fact is regenerated, because there might be a possibility that we are obtaining better cost, more cost effective explanations of that particular fact.
Hello, I'm Anamitra Mukhopadhyay. I'll be taking over from here on. We have already seen how the logic grid puzzle is played. We have also seen the formal definitions and algorithms that are used to generate simple explanations for such constraint satisfaction problems. Now let's have a look at how these algorithms are applied to generate explanations for the solution of a logic grid puzzle. There are a few real-life observations, and based on those observations, the functions f and g can be fine-tuned. Here we have our first observation. In a logic grid puzzle, there are a set of clues and implicit constraints like transitivity and bijectivity. It is observed that transitivity and bijectivity are very easy to handle, unlike clues. For instance, in case of bijectivity, when one value for a given function is derived to be true, then all the remaining values are propagated to be false. Here we have such an example. There is a known fact that farfalle goes with arrabbiata sauce. It is marked blue with a tick. Since pasta to sauce relations are bijective, we can propagate new facts that all other pastas do not go with arrabbiata sauce, and these are marked orange with a dash. Since these implicit constraints follow such well-specified pattern, the target is to perform propagations related to these constraints first. For these, the functions g and f have to be designed in such a way that for all S1 not containing any implicit constraint and for all S2 having one implicit constraint, we have g of S1 is greater than equal to f of I, S2. This way, S2 will always be taken before S1 in the algorithm to select minimum cost explanation. We have the second observation that clues do not usually propagate alone. In most cases, they need to be paired with some implicit constraint, that is bijectivity or transitivity, and then they can be propagated. For example, consider the sentence, the person who ordered capellini is either Damon or Claudia. This is a natural language sentence and we can conclude that people other than Damon or Claudia surely have not ordered Capellini. But the AI system takes these clues as typed first order logic, and when we translate it, the logical sentence as given in the slide is not enough to conclude that Angie did not order Capellini. This fact can be generated only when, along with the clue, we also consider bijectivity on the predicate ordered. Now there is another observation that it is very rare to use two clues to derive new information. Even if there are, in most cases they can be split up into derivations containing only single clues. However, there might be cases where it is not possible to split up the clues, but such cases are practically very rare. Interestingly, the algorithms can handle these complex cases. So based on these observations, the functions f and g are chosen like this. The number 20 is taken here to be larger than any practical explanation size. Here in this example, the solver uses 3 known facts and 1 clue and several bijections to generate one new fact. The clue is the person who ordered rotini is either the person who paid $8 more than Damon or the person who paid $8 less than Damon. The conclusion is farfalle cannot cost $8 because if it does, the cost of rotini will be out of the cost bounds or take the values $4 or $12. But these will force one of Tangolini or Capellini to cost $16, which is again a contradiction. So, in this way, this AI system can give explanations for complex derivations like these. To sum up, this AI solver provides step-by-step explanations that indicates how the puzzle goes from one state, formally defined as partial interpretation, to the next state. That is, in each step, the system generates new facts from known facts and reaches the unique solution in the end. Here are the references we have used as reading materials for this presentation, and thank you.